In this video, we're going to discuss how you can relate momentum to the net force, and we're going to do that by using impulse. So let's consider the Newton's second law, F net equals the mass times acceleration, right? We can rewrite this as the mass times what the acceleration equals, which is the change in velocity over the change in time. But you might notice here we have the mass times the change in velocity, which we know that we just learned that momentum is mass times velocity, so the change in momentum will be the mass times the change in velocity. So we can plug in momentum here, and we get that the force net is equal to the change in momentum over the change in time. Okay, so that's one big equation that we'll use. And so now that we have this force equals the change in momentum over the change in time, if we multiply both sides by change in time, we get the force times the change in time equals this change in momentum. And what we call this, we can also say P final minus P initial, but what we call this change in momentum is we call it impulse. And so we'll say that the force times the change in time is equal to the impulse, which we'll denote as a J, which equals the change in momentum. So that is the other big equation, which is really saying pretty much the same thing as this, just giving this term a name. And so the impulse J is going to have the same units as momentum, but when you first look at it, you might think, okay, we have a Newton and a second, so you may see impulse units described as a Newton second, but if we break up what a Newton is, kilograms meters per second squared, times a second, these end up canceling and we get a kilogram meter per second, which is the same units as we had for momentum. So this impulse is also going to be a vector quantity, and it's going to be in the same direction as this net force, since this time is not going to change the direction. Okay, so let's look at a couple graphs relating using these equations. So let's say we were given a graph of the momentum versus time. Since we know that the force equals the change in momentum over the change in time, this is just a rate of change right here. This is just a rate of change right here. So if we have a graph of this, the rate of change is just the slope. So if we wanted to find the force given these two variables, we could find it by just using the slope here. So this would be whatever the slope is, would be F net. And like right here, F net would equal 0. And right here it would be whatever the slope of this line is F net. So that's how you could use the momentum and time to find the net force. And let's say we're given a net force versus time, or a force versus time. Since we know that impulse is just the force times the change in time, now we're multiplying these two together, which means that's going to give us the area. So if we're able to find the area of this, we can find what the impulse is. And so this graph is pretty common to see if you have if you're hitting like a baseball, for example. You'll have a short amount of time where you're applying a force, and if you find but your force won't be perfectly even throughout. But you might see this graph approximated as something like, you can either approximate it by finding the midpoint and taking the area like this, or you may even be given a graph that looks something like this, and you can find the area just using geometry. So that's something to be aware of for the graphs that relate to these equations. Alright, so let's do an example here using impulse and change in momentum. So we have Bob pitches a 0.5 kilogram baseball to Bill. Bill hits the ball straight back at Bob with a force of 1,500 newtons. The ball was in contact with the bat for 0.01 seconds and has a velocity of 22 meters per second when it leaves the bat. What was the speed of the pitch? Okay, so let's write out what we know. So we know the mass of the ball, which is 0.5 kilograms. We know the force, which is 1,500 newtons. We know the time, or the change in time that it was in contact with the bat, was 0.01 seconds. And we know the final velocity of the ball, which equals 22 meters per second. So let's draw a little picture here. So we have the pitcher, which is Bob, and then we have the batter, which is Bill. So Bob is going to throw this ball at Bill, right? So we have the ball here, and this is the V initial right before it hits the bat, and that's what we're trying to solve for. So that's our question mark. But Bob is going to hit this ball and going to send it straight back at them with a V final, straight back at Bob. So, and this force must also be in this direction because it's hitting the ball in the opposite direction. So now we need to define our directions here. So we'll call this direction the negative direction and this direction the positive direction because it's going to depend on where we have our momentums. So the direction does matter and your sign will matter because we're dealing with vectors. So now, since this pitch is coming in the positive direction, the final velocity, since it comes in the opposite direction, is going to be negative. So we can denote this final velocity as negative, but the force is also in that direction, so the force will also need to be negative. Okay, so now we can set up our equation to see if we have enough information to solve this. So we know the force times the change in time is equal to the change in momentum. And the change in momentum equals the mass times velocity final minus velocity initial, or change in velocity. So we have force, we have time, we have the mass, and we have the v final, so we have everything to solve for the v initial velocity. So we can go ahead and divide by the mass, and then rearrange the equation for velocity initial, and we will get the v final minus this force change in time over m. And if we just go ahead and plug in all the values we have, we can solve for the velocity initial of the pitch. So that'll be right before it hits the bat. And so if we go ahead and plug those in, we get an initial velocity equal to 8 meters per second. And that'll be positive since we denoted that direction of the pitch to be positive. So that's our initial velocity, and that'll be our answer. Alright, so that's everything with change of momentum and impulse. In the next video, we'll talk about conservation of momentum, which is a really important principle to solve most problems with momentum and really shows why momentum is so powerful in physics. So make sure you stick around for that, leave your questions down below, and thanks for watching.